Thank you very much. It's fun to be down here at a lunch and learn instead of coming down in an evening activity. And I definitely want this to be an interactive presentation. I've got more slides probably than we really have time to go through if I were to spend a lot of time on each one. But if you have questions as we go along, I'd certainly be happy to either entertain your question at that point or tell you that we're going to get to that topic in just a few minutes. But when Rebecca asked me what I'd like to talk about, I've got plenty of talks and presentations I've given over the years, either at the Cedar Rapids Amateur Astronomy Club or at the Public Library in Iowa City. But one of the things that I thought we could talk about are some of the big unanswered questions in astronomy, because there are definitely some things that we don't fully understand, that we're still learning about. One thing that I think is really cool, though, is when I go to scientific conferences, I do get to hear presentations about some of these topics. And one of the things that sometimes is said is that we didn't find anything, or the experiment didn't give us the results we were looking for. And it's really interesting to see a room full of scientists really excited about the fact that they didn't find what they were looking for, because it means they have to go back to the drawing board and start looking again, or thinking of a new way of trying to discover evidence of the theory that they're hoping to prove is supported by the evidence. So it's really kind of neat to see people excited about the fact that they didn't find what they were looking for. So I don't know if I'll have any answers today. This is really more of a discussion of the unanswered questions. I'll give you what I think are some of the potential solutions that we have. But yeah, there's still a lot of things that we don't know. So with that, I think we'll go ahead and get started. And I like to point this out to students and other people that I give talks to. Many people like to make pronouncements of the fact that we've learned everything that we need to know, and that we've learned everything, we're coming to the end of knowledge in a certain area. And of course, it's never true. Simon Newcomb was a mathematician. He was really a polymath. He was a mathematician and astronomer, but he preferred studying mathematics. He worked at the U.S. Naval Observatory, and in 1888 he made this statement that we're probably nearing the limit of all we can know about astronomy. And actually all the way from the time of the Middle Ages up to the early 1900s, astronomy was really a mathematical science, because so much of what we did with astronomy was we kept time, and we measured position on the Earth and tracked the motions of the planets and asteroids and so forth, which is all involves mathematics. So saying that we were coming to the end of astronomy probably was not an unreasonable thing to say from the perspective of somebody who was a mathematician. But within just about 25 years or 30 years' time, these are all of the things that we discovered and mysteries that we began to solve. Within just about 12 years was the time that the quantum theory of matter was formulated by a number of people, including Niels Bohr and Albert Einstein and Max Planck. A number of great scientists discovered that there's a lot more to matter than what we can see with the eye, and there even were particles that they didn't know existed. So they discovered subatomic particles. When Simon Newcomb made that comment, they didn't even know the structure of the atom. The proton and the electron hadn't been discovered yet. They were hypothesized as being objects that exist because we knew negative and positive charge exist, but the particles themselves hadn't been discovered. And I made a mistake there. It should be new views of space-time. Albert Einstein formulated a new view of space-time that we often refer to as special relativity, and then a new formulation of gravity that extended the work of Newton that is known as the general theory of relativity. Shortly after the general theory of relativity was presented in 1916, astronomers discovered galaxies beyond our Milky Way, and that the universe is expanding. All of that was discovered by the 1930s. We've discovered other forces of nature besides gravity and electricity and magnetism. We'll talk a little bit more about them in a few minutes. And throughout the 1930s up into the 1940s and even beyond that, we began to understand more about how stars generate energy and how stars evolve. And that's still an ongoing problem because stars are always confounding us, because there are many more types of stars than we imagined, and they all behave a little bit differently. So clearly there were plenty of things that still needed to be discovered and had been discovered in the time that since 1888. But these are the things that I thought I would kind of concentrate on this afternoon. Three of the bigger mysteries, and as I was telling Rebecca, they all sort of relate to the dark, which is odd because astronomers deal with analyzing light, but all of these in a sense have something to do with the dark. One of them, questions that we have to ask is there more to the universe than we can actually see? And that is something that astronomers have begun to realize since about the 1930s, that there definitely seems to be more to the universe than is present in the visible light that we analyze. Even just 2 years ago, we discovered the existence of gravitational waves, which were actually hypothesized by Einstein back in 1916. So 100 years after Einstein hypothesized their existence, we finally had the technology to detect these incredibly tiny ripples of space-time that we call gravitational waves. So that's one example of something that we couldn't see, but we now understand. There are others. Are there other forces at work in the universe than the forces of nature that we understand today? And then we're often wondering, are there other planets even within our own solar system? Or are there other planets beyond our solar system that could support life, other Earth-like planets? That's another problem because they're very faint and very tiny and really hard to see. So in a sense, all of these mysteries involve analyzing the dark rather than the light. And the first one that I mentioned, is there more to the universe than we can see? The answer is yes. We refer to this today as dark matter. It was first theorized by an astronomer named Fritz Zwicky back in 1933. What Professor Zwicky had noticed is that when he looked at galaxies in clusters, and these are, immensely far away, hundreds of millions of light years away. So the light has been traveling hundreds of millions of years to reach Earth. But when he observed the galaxies within these clusters, he noticed unusually high velocities. Now, these galaxies should interact with each other gravitationally, and using Newton's law of gravitation and the newly formulated law of gravitation that Einstein formulated, and our understanding of the motion of galaxies through something referred to as Kepler's laws of planetary motion, which actually applies in cases beyond planets, we should be able to predict how fast galaxies move within clusters. And yet Zwicky saw velocities which were much higher than should have been possible based on the amount of light that the galaxies were giving off. And the reason I say the amount of light is if we see how much light galaxies are giving off, and we know how far away they are, we can compare that amount of light that all of these galaxies are giving off to the amount of light our sun is giving off, and estimate how many solar masses of matter is within the cluster of galaxies. So we can, through some pretty sophisticated calculations, estimate what the mass of all of the visible material is in the galaxy. And what we found is that the amount of mass necessary to produce the velocities that were determined was maybe 100 times greater than the amount of visible matter that was there. Now, Zwicky first found 400 times more mass than was visible. We've since refined that to about 100, but still being off by a factor of 100 is a big deal. So if you've got you need 100 times more matter in that galaxy cluster to account for the motion of the galaxies, something beyond visible matter has to be present. So we didn't know what it was. But there was more evidence, even with our own galaxy, that this must be true. Here's an artist's conception based on the best NASA data of what our Milky Way galaxy looks like from overhead. And what we've discovered is that stars near the edge of our galaxy should be orbiting slower than the stars near the center. We see the same thing within our solar system. Mercury is the fastest orbiting planet, Venus is a little bit slower, Earth is slower still, and out at Neptune is the slowest orbiting of the major planets. And if we go beyond Neptune, those objects will orbit even slower. So orbital speeds decrease at greater distances. But what astronomers have discovered is that the stars at the edges of galaxies actually are moving faster, or at least at the same speed as stars in the middle of the galaxy, which didn't make sense. So the rotation speeds of these stars, as they move around the center of our galaxy, was higher than expected. Here's one example of a galaxy. It's known as NGC 6503. And if we look at all of the visible stars in that galaxy, we call that the disk of the galaxy. And so if we look at the velocity of the stars in the disk, based only on the amount of light that they emit, we would see this curve that is the dashed line labeled disk. That's how fast we would expect the stars to be orbiting at different distances from the center of the galaxy, where 0 is at the center, 30 is out at the very edge of the galaxy. So that's the radius of the galaxy. And you see a very clear decrease in the speed of the stars in the disk of the galaxy. The farther out you go, the slower the stars are moving. That's exactly what we would expect from the work of Newton, Einstein, and Kepler. But what we actually see is the curve that is up at the top with all the little arrow bars on it. So all the ones with those little tails on them, that is the actual rotation speed that we get. Not even close to what we see with the disk of the galaxy. So in order to get the rotation curve of the stars and dust in the galaxy that is represented by that curve with the little dots and the arrow bars on it, we have to not only add the speed of all of the stars that are in the disk, we have to add the dust and the gas that is present in the galaxy too, which is the little dashed line down there. And the only way the disk and the gas components add together properly to produce that curve that goes along at the top is if we add that other one that's labeled halo. Halo is the invisible matter that makes up the galaxy that we can't see. That's what we call the dark matter. And we call it a halo because it extends far beyond the edge of the galaxy from what we can figure out. So it's really a halo of dark matter that surrounds the galaxy, and it pervades the entire galaxy. In fact, it's probably in this room right now, and it's probably inside of us. So the entire galaxy is filled with dark matter, and it extends out beyond the galaxy's visible edge in a large halo. So if we add a halo component in there, we get the kind of results that we would expect of that curve up there that is the actual rotation curve. But that doesn't tell us what the dark matter is. So that's really kind of the challenge. But there is also other evidence that the dark matter exists. One of them is something that is called gravitational lensing. This was hypothesized by Einstein. At least one form of gravitational lensing was hypothesized by Einstein about 1917 or so. But then another vision of that using galaxies was hypothesized by Fritz Zwicky in 1937. And basically what it says is that if you have a massive galaxy that is closer to you, that massive galaxy will warp the space around it and distort the light of a more distant object. Basically, that nearby galaxy acts like a lens, and it actually focuses the light of the galaxy that is much more distant. But if you can actually measure the amount of the distortion as if that nearby galaxy were a lens, if you measure the amount of the distortion, you should be able to figure out what the mass is of that nearby galaxy, because you know how much it is distorting the light of the more distant galaxy. So you can figure out the geometry of that lensing event and see how the distribution of matter within that lensing area is related to the visible light. So I'll show you some slides of that. But to kind of give you an idea of how that works, this was Newton's view of gravity. We have the Earth and the Moon right here, and he sort of envisioned gravity as an instantaneous force between two objects that is related to the amount of mass each object has. So it's an instantaneous force. Some people have often described it as kind of a spooky action at a distance. In other words, a force at a distance. It was instantaneous. Somehow the matter of the Earth and the matter of the Moon knew enough to attract each other. That was his view of gravity, but he honestly admitted he did not know why gravity worked. In his famous work on mathematical physics called the Principia, he actually wrote Fingal hypotheses, which in Latin means I feign hypothesis. I do not understand. So he actually admitted, I've explained the cause of the tides, I have explained the motion of the Moon around the Earth and the planets around the Sun, but I have yet not figured out an explanation for their causes. I do not feign hypothesis. So he did not know what caused gravity, although he gave us a mathematical relationship that works perfectly well to explain and predict the results of that gravitation. Well, Einstein knew that was a bit of a problem, and so he worked on a generalized view of gravity. We call that the general theory of relativity, in which he completely reformulated how we view space and time. And instead of having Earth and the Moon on a flat plane, almost like a chessboard. What Einstein said is that the mass of the Earth and the Moon actually distort the space-time around them. A way to envision this would be to think of what happens on a mattress if you were to sit a bowling ball on a mattress. And a bowling ball, which is fairly massive, would make a pretty large dent in a mattress. And if you sat a golf ball next to the bowling ball, the golf ball would make a very tiny dent in the mattress. It has a very small mass. But if the bowling ball and the golf ball were placed close enough together, the golf ball would roll towards the bowling ball. It would roll down that little well, just like an object falls towards the surface of the Earth when you drop it. Einstein said gravity is an illusion created by the curvature of space-time. And an object stays in orbit if it has a forward velocity that is great enough to counteract the tendency to fall towards the object that it's orbiting. So he didn't require a spooky force or action between two objects. It was simply a matter of the geometry of the space-time. And it was the geometry that determined whether an object stays in orbit, or whether an object is not in orbit, or whether an object falls to the surface of a planet, or whether an object floats freely out in space. Well, it's that curvature of space-time that we can use to understand gravitational lenses. Now, it sounds like an interesting idea, but it actually was tested. We know that space-time does curve, and the first test of that came 3 years after Einstein formulated his theory of general relativity. An astronomer named Arthur Eddington tested this, and he actually used a solar eclipse for the test. He knew that there would be a total solar eclipse in 1919, and so what he imagined is you could do a test. Einstein had proposed this as an idea to test his theory. If you were to take a photograph of the sky where the eclipse would occur, but if you took the photograph of that area of the sky 6 months earlier, the sun would be nowhere near that grouping of stars. The moon wouldn't be there either. You could just take a photograph of that grouping of stars one night, and then 6 months later, when the sun and the moon are in that position in the sky, and the sun covers up the moon, sky goes dark, and the stars are visible. Take another photograph of those same stars with the sun in the center of the star field. And what he discovered, as Einstein had predicted, is that the positions of the stars were different when the sun was in the center of the field of view than when the sun was nowhere nearby. And that was because the light from the stars was bending as it moved around the sun's curvature of space-time produced by the sun's mass. And here we see Earth down at the bottom. Now the star actually is directly behind the sun, up above the letter N in Eddington. So that's actually the real position of the star. It's emitting light in all directions. The light, as it passes the sun, is caught by the curvature of the sun's gravitational field and bends towards Earth. But we don't know the light has bent. So the illusion that we see is that the light followed a straight line, and so we observe the star out of position above the word Einstein, when in fact the star is actually between the word Eddington and test. If the sun were not there, the sun would be in, or excuse me, if the sun were not there, the light would actually travel in a straight line, and we would see the star in its real position. But when the sun is there, it appears to be in the observed position because the light traveled around a curved path, just like light going through a lens bends to a focal point. So we see this all the time. This is something scientists have made use of for many, many years. We even communicate with spacecraft and make use of this curvature of space-time, and we can track the path of the Voyager spacecraft as it leaves the solar system, because sometimes Voyager is behind the sun from our perspective. And we know where it's at, and we can actually see the effect of its radio wave bending as it goes around the sun's gravitational field. Here's what that gravitational lens looks like when we have a nearby galaxy and a farther galaxy. The white lines are the rays of light that are produced by the galaxy, and notice that the rays of light, as they travel towards Earth, are bending in the space-time around that nearby cluster of galaxies, and the light is bending. Some of the light, indicated by the red lines, bends so much that the light rays converge at Earth, and we get an image of that galaxy. But we don't get just a single image of that galaxy, we get multiple images of that galaxy. So here's an example of a lensed galaxy. and actually it's several objects. We have a nearby galaxy in the center of the field, that is the yellowish red galaxy. And then I have circled a couple objects, some in lighter yellow. And if we actually look at those objects circled in lighter yellow, and we analyze the light of them, astronomers find that they are absolutely identical, which to us tells us they're the same object. Because the light, when we analyze it, is spectroscopically identical. The objects that I've circled in blue are primordial galaxies. We call them quasars. But again, when we look at the light from those 4 objects that are circled in blue and we analyze them spectroscopically, absolutely identical. No difference. So that is telling us that those 4 images are actually the same object, and the light has been bent through a gravitational lens that is produced by that nearby galaxy that is the yellowish one. So we don't see the more distant object, we see images of it that are multiplied as they pass through the curved gravitational field. So we know something is causing this. Here's another example of a gravitational lens, and you can actually see these kind of bluish arcs. They're not complete circles, but they're kind of bluish arcs. Now we have seen some where they almost look like perfect circles. Those are called Einstein rings. But we have these bluish arcs. We have a nearby cluster of galaxies, that are in yellow there. And the figure on the right is a map that was constructed by the astronomers showing the distribution of mass that is necessary to produce the imaging that we see on the left. So the left is the true gravitational lens. The image on the right is actually the mathematical model that shows what distribution of matter is necessary to produce that image. And the bright parts that are the tall spikes, those are the galaxies themselves. But notice that the galaxies have tall spikes, but as you get down towards the bottom of the figure, they flare out. They've got little bases on them. The little bases on the bottom where they flare out is the dark matter halo. But the entire area is not flat. The entire area has a curvature to it. So that also tells us that within that entire area between the galaxies, not only do the galaxies have halos around them, indicated by the flaring out, but the whole area has some kind of curvature and distribution of dark matter that is represented by the curvature of this surface at the bottom. So yeah, I just put another image up here of a galaxy cluster there. Here is the galaxy cluster. And because of the lensing that is occurring in this image, and they're a little hard to see, but there are some faint blue arcs in there. And if we actually were spectroscopically analyzing the galaxies and the image in the image here, we'd see that some of them are identical. So they must be images of the same object. But adding on top of that the dark matter, here is the distribution of dark matter that produces the kind of gravitational lensing that we see. So you can kind of see that it is clumpy, and it does tend to center around the galaxies themselves. It's not quite as evenly distributed out in the space between the galaxies. So these are some of the candidates that people have proposed, and a couple of them have been ruled out. One of them is that maybe the dark matter that we see in this distribution is just really faint objects. Maybe it's a bunch of planets, or maybe it's black holes, or maybe it is very faint stars that we just can't see, or maybe it's just very, very cold dust. They refer to that kind of material as massive compact halo objects. They're out in the halo, they're massive, but they're cold, and they're just not giving off any kind of light. So those are referred to as massive compact halo objects. That has kind of been ruled out, actually. The other possibility is that they are weakly interacting particles. They interact through something beyond gravity, and then another possibility is maybe the view of gravity is wrong. We've ruled out these massive compact halo objects within the last 15 years or so. We've searched for low-mass stars. We've searched for black holes. We've looked at dust and gas. We've looked at things that are beyond the range of stars, that are very dim objects, not quite planets, not quite stars. We call them brown dwarfs. And none of these add up to enough mass to account for dark matter. So what they call weakly interacting massive particles. Some people have called them WIMPs. These weakly interacting massive particles are particles that only are involved in what we call the weak interaction. It's a force that is similar to that is involved in radioactive decay. And we do know of particles that are weakly interacting particles. These would be much larger than the ones that we've already discovered, but they seem to be the best candidates. And they could actually be very cold and very massive. So we think that these weakly interactive massive particles, they're actually related to neutrinos. They're a type of particle that would be weakly interacting. Some of you may have heard of neutrinos. They are the best candidate right now. That's where scientists are actively working. But we haven't had a lot of luck at finding them. One of the possibilities is directly detecting them by making experiments that detect them directly. Another way is detecting them indirectly through their effect on other ordinary matter. That's another possibility. Another possibility is make them. That's what the Large Hadron Collider is trying to do, is make these weakly interacting massive particles. And then another possibility, which I don't really know much about, but this is a new area of study, is looking for the very, very first generation of stars that formed just a few 100 million years after the universe began, because those stars would behave very differently than stars like our sun, because the distribution of dark matter was different in the early universe than it is today. So I don't really know a whole lot about that, but they call them dark stars. Basically, it means that they're just stars that have a large amount of dark matter in them, because they formed at the very early stages of the universe's formation, when the universe was much more compact. So those stars would be different than the stars that we see today. We have found one star just within the last few days, which is the most distant star ever observed. It's 9 billion light years away. A single star 9 billion light years away. That's a distance of about how far away a star would be when the universe is about 30% of its current age. So if we could see stars that were created, let's say, 13 billion years ago instead of 9, we would be getting closer to that first generation of stars. So that one was actually seen through a gravitational lens. It was just incredibly lucky that this one star was in the center of a gravitational lens, and it magnified the image enough that we could see it. Dark energy is something that is somewhat related to dark matter, but astronomers have known that the universe is expanding. They discovered that in the 1920s. Edwin Hubble figured that out about 1929. So we know the universe is expanding, which indicates it had a beginning event, something that caused the expansion to occur. But what astronomers discovered in the 1990s, to their surprise, is that not only is the universe expanding, but the expansion is accelerating. It's speeding up. Something is causing it to speed up. They don't really know exactly what is causing it to speed up, but it is something that we call dark energy. There is some repulsive phenomenon, some repulsive force, if you want to put it that way, that is causing the universe to accelerate. And we have since discovered 4 forces in nature, and everything in nature can be described as some combination of these 4 forces. We've got gravity, we've got electricity and magnetism. We also have something called the weak force, which relates to those weakly interacting particles, which is related to radioactive decay. And then there's another force that we don't think about, but it is actually extremely important, is the force that holds nuclei of atoms together. Like charges repel each other, but yet nuclei of atoms are packed with protons that are all positive. What stops the nucleus from disintegrating, and what makes atoms stable? It's something that we call the strong nuclear force. And these forces have all been studied really, really carefully, in depth for many decades, nearly a century now. But this repulsive acceleration to the universe's expansion indicates that maybe there is a 5th force that we haven't seen before. And maybe that 5th force only comes into play over immensely large distances, the distances between clusters of galaxies. So we still have to figure out what that 5th force is. But the crazy thing is, if we look at all the visible matter in the universe, all the visible matter in the universe actually makes up those little slivers. The 0.4, the 0.6, the 1.2, the 2.6. That's everything that we see. The dark matter is the larger 25% yellow wedge. That still isn't enough to account for the behavior of the universe. The accelerated expansion, which is indicated by this thing that we call dark energy, tells us that the matter and energy in the universe that is dark energy could be as much as 70% of what makes up the universe. So everything that you see when you look through a telescope or you look at a photograph of the universe, a Hubble Space Telescope photograph, everything that we see makes up only about 4%, which are those 4 little wedges. So there is a lot that we don't understand, because we don't understand the big yellow wedge and we don't understand the much larger gray wedge. The gray wedge is the dark energy, the yellow wedge is the dark matter. So we've got a lot to figure out there. On to the planets here. We're searching for planets beyond Neptune. One of the possibilities is using a very large camera on a newer telescope. It's called the Blanco telescope in Chile. It's a dark energy camera. So the camera was actually designed to look for evidence of dark energy, but planets way beyond Neptune are going to be dark. So we want to have a camera that's really sensitive. So let's use that camera. This camera was designed to map millions of galaxies. In one image, it captures so much of the sky that it's 14 times bigger than the full moon. That's a lot of real estate for one image. One image is a year's worth of data at another telescope, and they can capture a year's worth of data in one night. So they want to get a lot of data, and they discovered this object called 2012 VP113. At that time, it's not given a name yet. It is the object that has the most distant close point in its orbit to the sun. It's not the most distant object, but it is the one that, when it is closest to the sun, is still farther away. And that distance is shown here. So here we have some of the other objects that we've discovered. These are all way beyond Neptune, by the way. That little circle down at the center that looks like it's glowing, that's not the sun. The sun is at the center, and then the outer ring of that, you see kind of a brighter ring, that's Neptune's orbit, the 8th planet from the sun. And Neptune is 30 times farther from the sun than Earth is. So that little yellow circle, 30 times farther from the sun than the Earth is, and these other objects, these are the orbits of these other objects that have been discovered beyond the orbit of Neptune. They're actually even beyond what is called the Kuiper Belt. The Kuiper Belt is a second asteroid belt. And Neptune is at the inner edge of the Kuiper Belt. Part of the reason Pluto was demoted is because we've discovered so many objects in the Kuiper Belt that are larger than Pluto. Pluto doesn't really meet the classification of a planet anymore. It's a Kuiper Belt object. It just actually, by coincidence, was discovered in 1930 before we knew the Kuiper Belt existed. So it was actually given a designation of a planet long before we understood the neighborhood in which it was discovered. But the Kuiper Belt is a second asteroid belt. These objects go way beyond the Kuiper Belt, and what astronomers have noticed is that most of their orbits line up in such a way that their closest point to the sun, a point called perihelion, seems to congregate in one area of the solar system. And if they congregate in one area of the solar system, it could be coincidence, or it could be evidence that something unseen is gravitationally shepherding them. We've seen that kind of shepherding effect in the rings of Saturn, and how other moons orbit planets and have these kind of gravitational interactions. So maybe there is something that is gravitationally shepherding these outer objects into these orbits that we see right here, and one object that could be doing that is shown with this yellow figure right here, which we just provisionally think could be the 9th planet in the solar system. Sometimes they call it Planet X, but it could be the new 9th planet in the solar system. If it does exist, its average distance from the sun is 400 times greater than Earth's distance. That's what the 400 AU means. 400 times larger than the Earth-Sun distance would be its average distance from the sun. The length of time to complete one orbit, in other words, the year on this object, would be 20,000 Earth years. It could be the object responsible for controlling the motion of these objects in the outer edge of the solar system. So we think this object could be out there, and I honestly don't remember the mass. I'm trying to think how big this object is, and I don't remember from the paper that I was looking at if they think it's what they might call a super Earth, or if it's somewhere in that range of maybe roughly the size of Neptune, or somewhere. But Neptune is about 125 times the mass of Earth. So I don't know if it'd be, or 20. I I don't know if it would be quite that large, but yeah, I'm sorry, not 125 times the mass of the Earth, not 125. So maybe a super Earth is what they might call this. This actually shows you the Kuiper Belt. Here's the orbit of Halley's Comet, shown there. So the Kuiper Belt goes beyond Neptune. Beyond that even is a larger cloud called the Oort Cloud. It goes a third of the way out to the nearest star. And so the Oort Cloud is another possibility where we might find many, many distant objects in our solar system. This is what we know today. Around other stars, we have confirmed over 3,700 planets. We call them exoplanets. That's the confirmed number. That number will go up. There are other ones that are still being investigated, but that is the confirmed number. The closest exoplanet actually is only 4 light years away. It's orbiting the star Alpha Centauri, actually the third one in the system, called Proxima Centauri. So the closest star outside of, or closest planet outside of our solar system is actually orbiting the closest star to our sun. These exoplanets, however, fall into basically 3 main categories. The first ones we discovered were very large, easy to find because they have a lot of mass. They call them hot Jupiters. They call them hot Jupiters because they orbit much closer to their stars than Jupiter does to our sun. They orbit even inside the orbit of Earth in terms of a distance. So they would be very hot planets, but they're massive like Jupiter, so we call them hot Jupiters. We've also discovered another grouping that we call mini Neptunes. They're kind of about the size of Neptune, which, like I said, is about 25 times the mass of Earth. So they're not nearly as big as Jupiter. Jupiter's 300 times the mass of Earth, so Jupiter's huge. So mini Neptunes are about 25 times the mass of Earth. And then we found a few super Earths, which are planets between 1 and 2 times the size of Earth. So far, we've only found 10 that are within what we would call the habitable zone of their stars. The habitable zone is the area in which water can exist as a liquid because of the amount of heat and energy that the planet receives from the star. So the habitable zone is where we would find liquid water. In the case of our solar system, it's roughly from where Venus is out to Mars. That's the area in which water can exist as a liquid in a planet's atmosphere. So we found 10 so far. It's a pretty small number, but we've only started to look, and we've only just begun to develop the technology to find really small planets. Earth is so small that you could fit 108 of them across the sun's equator, and if the sun were a gumball machine, you would get 1.3 million Earths inside of it. So we're looking at really tiny objects. So looking for these really tiny Earth-like objects is really difficult. For one, you've got to block out the light of the star, so that the star doesn't overwhelm the camera. So you've got to block out the light of the star, and then you've got to look for small, faint signatures of light. Now here's the breakdown. So I said there are the Jupiters, hot Jupiters, there's the Neptunes, there's the Earths. So this is what we found so far. We've found a number of super Earths and mini Neptunes. We just haven't found them necessarily within the habitable zones. And part of the problem is we have to figure out what kind of star to look for. We thought at one time you might find planets around the most common type of star, which is called a red dwarf. It's a small star about 1/10 of the mass of our sun. It's a cool star, so it's reddish in color. Our sun's nearest neighbor is a red dwarf, and it has a planet around it. And so astronomers would thought that let's look around the most common type of star and see what we see for planets. And we do find planets around these red dwarf stars. We find lots of planets. But the problem that we've also discovered within the last 10 to 15 years of studying these red dwarfs is that they're really, really violent little stars. They're not stable like our sun. So we thought they would be really stable, boring stars. Planets could form. There'd be a long time for evolution to evolve or evolution to occur on the planets. But what we find is that they're really violent little stars. They're prone to really, really powerful outbursts of solar storms, like our sun. Solar storms give us the northern lights. Really strong solar storms can knock satellites out of commission, and really, really strong solar storms around planets could rip off their atmospheres if the planets don't have magnetic fields. So if a planet doesn't have a magnetic field and it's around a little red dwarf, it could have its atmosphere sheared away in tens of millions or hundreds of millions of years. So we want to find small planets that have magnetic fields to protect them from their stars. Then they need to have an atmosphere, as far as we know, to have life on it. And those don't always seem to be compatible with the red dwarfs. Those planets may not have magnetic fields, or their stars are so violent that they just rip the planetary atmospheres away. So we're starting to look around the solar type stars that are about the temperature of our sun, and we're just now really beginning that search. But so far what we've discovered is that and these are two examples, one of them was found by the Kepler telescope, or both are found by the Kepler telescope, and one is Kepler 452, that's the name of the star, and the other one is Kepler 22. The lowercase b indicates it's the second planet from the star. We use the lowercase letter to indicate the planet. And what we've discovered when we look at these planets is that notice that there's that dip at about 1.75. It's between 1.5 and 2. There seems to be a dip in the number of planets that are that size. So that's telling us there's a different process going on to create the planets that are less than 1.75 times the radius of Earth, and those that are more than 1.75 times the radius of the Earth. The smaller ones are formed by processes that make them rocky. The ones above that divide are being formed by processes that involve ice that make them gaseous, like Neptune. So there seems to be something going on in the planetary formation process that is dividing them into rocky planets and the gaseous ones. And that divide seems to be right about 1.75 times the size of Earth. So that's one thing that we're beginning to learn, but we need to learn more about them. And we also need to find out if they've got atmospheres. This is where a new mission that was just approved a couple weeks ago by the European Space Agency called Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey Mission. Ariel is going to be looking at over 1,000 exoplanets, specifically looking for metals in the planet, which would indicate that they're rocky and Earth-like, and the compositions of their atmospheres. So this is going to be a mission that takes place in the late 2020s. It's going to take a while to build it. But in the meantime, we'll have other telescopes that are being built. The James Webb Telescope is one, the LSST, another large telescope. They're going to be looking not only in invisible light, but in infrared, which is heat. So they're going to be looking beyond the visible range in the infrared to see if there are heat signatures from these very, very faint objects. So that's another place to start looking beyond the visible light, is looking at the heat signatures that these very faint objects are giving off. So there's a lot of potential for maybe finding Earth-like planets, but first we have to know where to look, and we have to start investigating whether they even have magnetic fields and atmospheres, and that's what this mission is going to. But it's very complicated to look for these things, but as I was saying, mostly what we're trying to do is look for things in the dark rather than things in the light, which is really a big challenge. So I think that kind of wrapped it up there, but if you have any other questions, I'll be happy to take those. Or